Hello, hello. Hey, look at that. That's me the other day. And today, that's me today. Hello, how's it going? I'm Junchan, and we're back on stream for some Comonadic Explorations. And yeah, last time, let's go back to the screen, but something's up with Visual Studio Code. I'm not sure what is happening here. Looks like maybe I'm going to have to restart it. Maybe I can cancel. Yeah, I probably can. Okay, so let's see. Let's cancel this. Can we? Maybe not. Okay, I think this guy seems to be stuck, and I think that's the guy we want to use. So let's just quit. Well, we don't need to save the configuration. Save the changes we made to main. Well, unfortunately, we're not going to be able to do that. So let's see which VS Code processes we need to kill. Quite a few. 14 and 15, and who else? VS Code, watcher service. There's too many things. Can I just what is it? pkill code, or which one is it? Bootstrap fork? Yeah, that's not gonna work, is it? Can I not force quit my cancel? No, why did I do cancel? I didn't want to do cancel. Save. Okay, I've done that just earlier. I'm a little bit yes, so that's the one I think that we can't close right now. Yeah, so this should be one of the only ones remaining. Hopefully that's TypeScript. I have no idea. Let's try and kill that guy. Pure script language server. That's probably good to also remove. And okay, it sounds like it's mostly all our pure script related ID. Maybe the problem is now I'm in an Xshell with the pure script version 14, which we installed last time, but I suppose that in the version that's installed globally is still 13.8, but that's not really what we're doing right now. We're going to need to kill a few more of these processes. Yeah, here there's some code there. So can't I kill pkill code? Yeah, I can. Okay. Oof. So we open the pairing. We open in a different window the hold on, is this related to it could have been related to the fact that my external hard drive was taking a little bit of time to start. That could have been responsible for the Visual Studio Code being hung up. Okay, so where were we last time? Last time I think I was trying to basically recap a little bit where things were with the work I'd done with Comonads. That's a bit weird that it's only 0727 there. So did I just duplicate in the other folder? It's possible. Okay, weird stuff. Hold on. Yeah, no, I don't want to read from the stash. That's my mistake. I want to read from my home directory. There we go. And here we have the 0810 thing we were working on last time. Okay. So, wow, that's a lot to get back to what we're doing. So what we're doing was continuing to play with the Comonadic UIs and trying to understand the pattern between explore being also something that actually is a co-free monad function, which has a signature which matches a bit the pairing, which takes a free F. It matches Zap. So let's go take a look at Zap. Pairing, Zap, F, A to B, and GA. So our F is a free F, and our G is co-free G. And so free F, A to B, and co-free GA gives a B. And that's exactly Zap. So I think what that means, and I hadn't considered that yet, is that explore actually equals, especially in the class version, if I succeed in doing that, yes, it equals pair free T co-free T. Basically, it's the pair. Explore is the pair instance or the pairing instance for free F co-free G. So that's the guy here. And look at this. It is actually pair F is explore Zap mapping F. Oh, right, because we are not exactly using, because we're using a slightly different formulation for Zap, we're using pair. And so instead of F A to B G A, we have an ABC, an FA, and a GB. And so we take an F as an argument of pair, and then we then map F, and we do explore. We explore Zap. And what's also, hold on, I'm just a tiny bit confused here. We explore using, so is this, how does this associate? I think we map F first. And then we explore Zap. Zap being this fx to y, gx to y. So Zap is Zap is actually pair dollar. So that's explore per dollar. Is that right? Yeah, but it's the pair instance for the underlying F and G. So it's a bit like explore unrolls the free and the co-free, and then the zap map F goes into the F and the G. And the pair free T co-free T, which I think we lifted from Ed's code. Or at least from one of the libraries. The ones where there's a zap. Oh, well, that's graph. We're not going to need that. Yeah, okay, I think I can also let go of most of that stuff. Troubleshooting, installing PureScript the other day. So package and adjunctions, I think, and zap, and let's see, did it disappear then? I think it did, right? Version 1 didn't have zap anymore. Actually, it left data functor zap. Yeah, that's fine, but this doesn't really have this instance. Where did I get this instance from? So let me open a few more things here. Shared workshop, no, space, build, code, and I think it's somewhere here. Yeah, the not Comonadic Playground, but Comonadic UI. Basic. This guy had the pair free T, co free T. Okay, so yeah, that's where I took the code from. I mean, this might actually just come from PureScript pairing. Why wouldn't it come from PureScript pairing? Okay, and data functor pairing, and okay, well, apparently not. Most definitely not. So let's make sure that we understand where things come from. Data functor pairing. Yeah, that's right. Okay, so that's interesting. That is interesting. Explore. I want to see explore. So really, what I was going to say before checking a bit where I was at is that we do have a few explorers that there's one explorer that come from Phil's original formulation, which where I suppose we're going to also have to open that, and that's going to be in experiments and Comonad composition POC. In the original formulation, explore was this this thing. I tweaked it quite a bit, so it's now different, but it is this, and it's. I was saying last time that the Arthur Xavier formulation of explore is maybe a little bit. If not, it follows a maybe slightly clearer pattern. We have explore in the UI library. So if we go check this out here, we have in the UI library, we have an explore here, which is an explore on components. And then we have a react.explore, which is a React on React component, which wraps UI component. It determines a carrier type of our React element. So this is more general for any A, but applied to React, it uses the UI.explore, but it passes it a write function which knows how to specifically write the React state. And as I was saying last time, I think this is really peculiar to the fact that with frameworks like React, modifying state retriggers a render, and that's basically that means that this is the event loop right there. That's kind of waiting asynchronously for an event, a DOM event to trigger the callback that's being passed through this exploring machinery. And specifically, it's going to create the callbacks are going to call send, which are going to call write, and they're going to move according to whatever the movement in the base monad was. So and this in Phil Freeman's formulation, this was done with runco. And I think basically there are a relationship between runco, between pair, especially runco used with M, and especially runco passed to extend const state, which sort of moves the comonad forward. All of this is basically they're all related. Pairing, exploring, runco. And I'm trying to maybe untie this or try and find some other patterns, especially because I worry that this particular way to hook, like to create this async event loop, is really not easy to read, because like there's a double inversion of control thing going on where you pass basically your component itself is actually a comonad of handlers, and then you have this send function that's passed to your callbacks that then call the comonad of handlers with the whatever monadic action you passed. And all of this is very it makes control flow really hard to understand, I find. And so I was wondering whether it would be possible to rewrite this double inversion of control as something that's maybe more perfunctory or more arrow-like, maybe more FRP-like. That's been one of the early thoughts about this, and I suppose that in this case, I see one of the mechanisms in which maybe that would be a benefit to actually move towards more of a stream-like formulation for this. But I don't know yet how to do that, and I think they would be fairly difficult. So that's that. Then what we were trying to do otherwise was to apply this whole machinery to understand how we should deal with monadic effects inside a comonad transformer stack or inside this co-construction, because with the co-construction, we take a comonad, and in our case, it's let's say counter. We rename this counter interface. It provides us with the operations that the counter provides: change, count, or increment. So it's kind of an interface. And then one of the ways that this the Phil-Freeman's co-effect blog post proposed, and that's this one. That's kind of all the way there. Proposes to interleave monadic effect by using this co-t, which I need to rewrap my head around, because I need to understand better what is the interplay between the co-t and this co-free, basically this co-free compose MFA. Because then here there's a proposition that we do co-t of co-free compose MFMA, and I wonder whether all of this is actually well, first of all, I still don't have the intuition of why we have M's in both places. I think it's because this M is kind of on the return side of things. Well, this M here maybe is, I think this M is something that's in the co-free construction. So it's going to be interleave with each of the base functors. We're going to rewrap everything with an M. So that leads, I think, to us when we're trying to build a function like that, to do compose and then pure to get our M, and then our counter interface, which is our inner co-free, I think. Or is that right? I'm not sure that's right. Okay, I need to get myself back into what these things mean. Let's see. Move from the co-monad to the co-t monad transformer. So one question is, of course, could we make this work just like this? So here we'd have a monad transformer with the effect-based monad and the counter interface the counter interface comonad, and so in theory that should wrap the counter interface monad, but also allow it to do something in the effect monad. Is that true or not? Let's see if that's the case by trying this. So that types checks. I mean, does it type check? Am I actually running a ID here? Not clear. Error, connection refused. So maybe we need to delete this and restart. Starting ID server. We're trying, still connection refused. Oh, 0.0.13.8. No, that should be fine. Cache DB. Okay, I need to go into it and try and spec build. This was failing in the wrap free here, so I could send just a pure unit, and I think that will allow us to compile a little bit further. M. Right. Okay. Hold on. So let's reload the window. Resolve, starting ID, started, and it fails. Let's ask to build. Make a build. Fail to build. Build complete reloaded modules. And there we go. There we go. Okay, so right, so here I think we don't know how to write this instance yet, and then that actually builds. Oh right, it does. No, it does not. Oh, okay. So this is not. So apparently log effect doesn't type check, and neither does this. Right. Because we're treating. Okay, so but maybe that's fine. Okay, so let's go back to a non-monadic. So in that case, compose M is actually just counter interface increment, and we don't do, and we just increment unit, I think, and we need to parenthesize this and probably do pure here. Yeah, Koti. Yeah, probably do pure actually. No. Right, how's that going to work with the Koti transformer here? Because it sounds like we need to return MR. Or we need to pass a function that, given an A, we return an MR. Yeah, I'm not sure that that's going to work. So I think this means increment being passed an counter interface A. So that apparently is a function. T0 R1. Let's try and see if we can get the type checker to help us a bit here. Compose counter interface blah. Oh, don't need compose here. And that's effectar 0. So then I think we're good by doing increment unit. We are. Okay, so now we're back to wrap 3, I think, not working for us. Yes. And because that's because we don't know how to handle Coty counter-interface effect, which I think makes sense. So that actually simplifies, I think, our problem with this instance, because we only need to do the Coty W effect. I don't even know whether this is the instance we're looking for right now. We want to control a monad-free instance for Coty counter-interface effect, where f is counter-interface, and so f is any functor, okay, and w is the co-free compose effect counter-interface. I think that's because of the type of main that it didn't change. And I think we don't need to do that. Maybe not. I'm trying to see whether we can get rid of that M. I'm doing it in a very ad hoc manner. Like the one in compose MF. Basically, try to do just Coty, co-free F, MA, and see where that leads us. Because I'm not so sure about embedding the effects inside the comonad. And if it's sufficient to add a monad somewhere into that comonad stack at the base, then I think that's enough, because it's enough as long as I can, which might not be the case. Yeah, that the difference is going to be that I think my interpreter won't be able to be effectful if I do it that way, I think. And that was kind of convenient, I think. By the way, this should be effect here, right? I think I was toying with that the other time. But so now, indeed, we're in a bit of a pickle. And I suppose that's why we have co-free compose MF here, is because we're trying to have the same thing here and here. Meaning we're trying to say that the monad free of the thing that is a co-free of an F is a co-free of the same F. So I think I get it, but I'm really wondering whether we have to do that. It seems like that's too big language, as I've heard some smarter folks say. Meaning, I think this doesn't constrain how we define our monadic actions and how we define our interpreter enough. I think that's because in my ideal view, the monadic actions based or built on top of the comonad actually don't have effects. Hold on one second. I just realized the thing, I think. If that's the case, then they're just the co without the effect, and then I think the ink, that is the one we want, which is the kind of more verbose one, is just, as people like to say, lift co-f of ink prime, I think. But really, I'm not effect here as well. Yeah, and then not match co-free with compose effect. So let's look at what leaf_cof does again. It does take a cofa, and it does make a co-T co-free compose MF MA out of it. So the intuition, I think, is right, but hold on, that creates the co-free directly. Oh, okay, so but maybe that's fine actually, because if that's the case, then I think we don't need wrap free underneath. Then I think we can just say ink. I don't know, I'm imagining. Okay. Okay, send. It's the UI, so it takes the handler, turns the React element. Okay, maybe we need to keep the pure unit. Could not match type. Affected identity. Okay, there's an identity somewhere. Which one could it be? Let's see. Explore. That's particularly weird these days. There's effect here. Ink has effect in it. Well, if we pass counter interpreter pure, do we pass counter interpreter pure? We don't. We pass counter interpreter. Counters. Right, that's the fully unfolded type. It takes the interpreter, passes it to counter, and counter. Waits for an interpreter as well. And for some reason you think that there's an identity at play somewhere. Okay, let's try this again. Here you're saying what? You're saying you don't have that yeah, I think, yeah, that's definitely not wrap free. And I think the reason why we want wrap free is that we want an MA instead of an FMA. And yeah, I think we don't want the co-free thing. Yeah, I think that's a fool's errand. I was already rebuilding the co-free, but rebuilding the co-free at this stage when we're passing the step counter function. So no, not that. But then I suppose we could try and write a wrap free T function and see whether it takes us where we want to go. So in theory, I think it's supposed to take us from the F being the compose effect counter interface. I think let's try compose them. There might be an A. Compose effect counter interpreter of effect A. something like that to effect A. I don't know. Pretty equals something. Unknown type counter our interface now it's called. Okay. So that's really the type we want. Inc is a COTI counter interface effect unit. But when we apply to pure unit, it's wrapped into a counter interpreter. Yeah, I'm not sure that that's going to be the type we want here. Pretty unlikely, to be honest. Let's not put a type in there and reassess. It says T0. Yeah, so that's a different thing. Right. So hold on one second. What happens if I do this? Right, you have several problems, I suppose, like wrap free. I do use COTI here, but that's the same. Oh, that's where the identity came from. Yes, so if I do this and I do, well, then I suppose I need to go back to really my other definition. I don't really have a choice. And I need to do the compose dance. Then we finally back to still not what I was expecting. There's still an identity lingering right here. Maybe because of that. Do I need to COTI compose effect counter space as well? Oh, hold on. Yeah, how's this work? Because counter space is co-free compose effect counter interface actually. Right. It's not co-free counter interpreter. There's something wrong in that. It doesn't seem correct. It's co-free compose effect counter interface. Where is this identity coming from? I'll take a short break and be right back. Okay, so let's try and get this under control. the reason why we have identity here in the Coty part, so this seems to be expecting that the compose effect counter interface base functor is the base functor of the co-free thing here, which makes total sense, but for some reason the monad transformer thinks that it's in a different stack. Why would it think that? It would think that if wrap free, you would think that if the type that were given to wrap free led it to believe that, and ink wouldn't lead it to believe that, I don't think. Ink would be of the type with the effects in the appropriate place. So it could be the pure that leads it to believe that. Or it could be the external, the effects. Oh, yes. The fact that there's co here means that we are expecting identity at the end there. Right, so I need to be in Coty counter space effect. And then I need to be in Coty. So I was kind of close to it earlier, but I was not exactly there. And now we have effect here. Okay, so we are getting one step closer. And now I suppose we do have to write this this type class and try and find out how to write it. But now it's the right one at last. So here visibly I'm using, apparently I'm using sim to turn Perco around, and so what should be the type of this? You're saying it should be, so Coty F0 identity, it has the infer type identity because this is Perco and not Perco T, so Perco will, yeah, but we don't have a Perco T, and we've been struggling to try and write one. And so maybe we start with Perco, we inline it, yeah, except that okay, how are we gonna do that? Perco here takes as the F run Coty, which is pretty weird, to be honest. Well, how did I come up with that? And did I try and copy? I must have tried to copy this, right? Yes, and this does Perco run co. Interesting. Well, clearly I let's double check that we haven't mangled that too much. Vertical, and I think it looked legit. Yes, it does. Sorry. Okay. So calling this GCO is a little bit weird given the name of things. But we're trying to take an FMA, and so what's the wrapping thing? The wrapping thing would be the W, no? wrap free. No, it wouldn't. It wouldn't. It would be the co-free F, I think. Ugh. Wow, this is hard. Okay. So I think F is co of co-free F. Because that's the base F, then the base functor of the free monad that's equivalent to the co-free comonad that uses F as the base functor is, I think, co-free F. I think. So we're trying to remove a co-free F layer of an MA, but really it's a WA, right? But it's not a W because it's a co-WA. And so ultimately, I think we're trying to do that. Except that we are now doing that with M's. And so if we add a co-T in the equation, then all of a sudden we also have an M here, and we have an M here. Yes. No. Co-TWM A. Yes. Co-TWM. Right. So actually, yeah, that is really not obvious. Hold on. Also, shouldn't I be doing the compose thing? The compose one is the one that I want. Maybe it's simpler to do because, or maybe it's the only one that can be done actually. Okay, let's try and see whether we can copy what we're missing here. This guy. And see whether we can square that with this type. It's going to be pretty involved, but it kind of makes sense like this, right? The co-T and the co-free, and so on. So maybe we do an instance just for that, and maybe we try and generalize it some other time. So co-T compose. Okay, maybe we can make it M, F, M, and co-T. Yeah. Breathe. I think damn. I think maybe compose counter interface is the base functor. So I think we're just saying W here and that's it. But then, yeah, the W is this free compose effect, blah. And yeah, I think that's the case. So is that's overlapping, right? Yeah. Or yeah, maybe it's not overlapping. Monad free compose effect co-T. No, it's overlapping, of course. Okay. So right. Okay, so now we all still have an identity in there, but yeah, that's because of the pair co. And so what we were saying earlier is that maybe we can replace the pair co by its definition using good old equational reasoning. Maybe we, so first of all, there's this weird thing about the fact that the original pair co, like that this guy, and maybe we do the equational reasoning on this guy before, because that's just weird, because this becomes, so pair co F W co W, and then knowing that sim, yeah, just take the whole thing, so that's fine. So really run co with the co W, which is this, and then map F so map, and then run co is F, and then GCO is W. Hold on, not the right W. Is the no, it is. It's GCO. Yeah, it is the right W. Okay. And runco is what? Runco is just removing the. Okay, runco is actually pretty involved as well. Holy moly. Okay. But I suppose the thing is, if we have it like this, then can we just put runco T here and there and then it's done? No. Because unwrap co-free of RW is not going to be sufficient. I mean, this is going to be compose. This is going to be compose M, by the way. And to get to the W, we need to do the thing we were doing earlier, which is we need to execute M. And then we need to, then we have a W. Isn't that true? Well, it might be, but runco is still not happy. What's the difference between runco and runco? Runco takes the co-t and run. Ah, yeah, runco is now very complicated because of the identity transform. But before it was just run identity co. Or maybe it was just co, actually, to be honest. Yeah, that's what it was. So it was just removing the co-t. So if we apply it to hold on, we're here. If we apply to here, then when we map runco onto GCO being, I think, this thing, right? GCO is that. So when we map runco onto GCO, we just get the co-free F blah. We get the co-free F blah, not exactly. We get whatever is in the co-constructor. So this thing, the WAR, that's one of the important bits here. So let's get it down. So when we map runco onto the GCO, what we actually get is a function of cofree f cofree f is the W, and a function from, I think, co-WA to R. And now we try to unwrap co-free. And unwrap co-free takes WA and returns an FWA. And but hold on. Yeah, so I think it's just going to be the fact that we have these continuation based things. So the fact that our W here, our W is what's in the co, the outside co. Are we trying to create, which we want to be the co WA. No, so yeah, W is a W full of A to R's. So this has A to R's inside. And when we unwrap co-free, we go from WA to R's to I think co-free. This is so hard. WA to R, but the W is co-free F. So co-free F A to R. That's the W. And then it's still wrapped by an F. Then I guess it's wrapped by an F. And then we're trying to say that this thing somehow, I mean, clearly I got lost somewhere here. Because like in theory, then we just pass that to runco and then it will be good for some reason. Because as if this was a co, and that, no, so remember it's the sim, we'll flip the thing around. Flip will take our runco, and they will flip the two things that are expected, so we will flip yeah, curiously, it would make no sense with pairco, to be honest, especially the sim part. So maybe I should actually try and go back to this, even if I don't, yeah, maybe doing a pair Coty is not going to be possible, but so I need to double check my pair co here. My inlining of pair co. We did veer quite. I mean, I really can't make so much sense out of the. Or maybe we should do sim pair co first, and that's going to. That's going to maybe. Is that just going to flip things in a way that's understandable? You know what? Maybe it will, because here we're saying it would be pair co of co W and W, right? Yeah, but I think I need to have this interpretation of pair co here. Yeah, taking an A to B to C, and obviously using runco as this is where things are a little bit weird. They're a bit weird, but then I wonder whether there's some other equality. Like, I wonder whether this is actually yielding zap somehow. It just feels like that. Like somehow maybe pairco of runco is actually something known. I mean, it's really weird that it has two runcos, but yeah, I don't know if it's known. But so here, sim pairco should be taking a WA and a co WB, but it takes a runco as the function, and then that's the WA. So I think, yeah, I think really, but I don't understand why then. And can I try that? Why then? Why do the sim? Why not just? Oh, because runco. Oh, because of the order of runco. Okay. Okay, I was like, why not flip those arguments? But it's because runco actually because it keeps the A to B to C despite flipping the GA and the FB. So we can't just flip those two. It's a little bit more tricky than that. Yeah. Okay. So the use of runco as the pairing function is one of the weird things here. And I think this is fine, right? Therefore, sim really only turns the pairco around. So ideally, I also know what sim pairco FW COW is equal to. And I think it's not trivial. it's not just about flipping those things. Yeah, I don't have the wherewithal to go down into this particular type Tetris malarkey. So equational reasoning is not a dead end, but it's a narrow, really off the beaten path that I'm not sure I want to try and follow. So if that's the case, well, then I suppose that's not true. It's not. I think the way that this is associated is means that this is wrong. In fact, I am pretty sure. I can't just equationally replace pair-co here with its values because it's actually sim pair-co that has these values. So, and if I don't know what sim pair-co is, then I am still stuck. Whereas if I knew what it was, then I could actually write this. So you know what? I'm going to have to go down this rabbit hole that I fear. Okay. Not capital pair. Pair-co is this A to B to C. So that's fine, right? Hold on. No. Pair-co is the pair-co is a function from all of that stuff. Good. And sim pair-co is going to transform it into this function. So yeah, maybe I can equationally reason on sim. Where is sim, by the way? Where is sim coming from? From data function pairing. It is. So I can just equationally reason. Why do I make things more complicated than they are? Okay, so pairing. If we do sim of pair-co, especially of fw co w, then clearly it's pair-co of flip f COW W, which means that this is not this. This is pair-co of flip f is run-co W is GCO, and so indeed we just flip the things. So yeah, we just had to have an additional flip for the F. Yeah, I put it in the wrong place. It goes here. I think this is correct. How can I know? Maybe I can comment one of these guys. Oh, I seem to have actually completely removed the thing. This guy, I believe. It's the monad free instance, but for co. So yeah, I'm in the wrong place. That's what's going on. Here, this guy. Can I comment you? Right. well, you're right, I could if I did something a little bit temporary, but it's just to type check. Maybe I should just be confident and just say, yeah, no, that's it. That's Perco flip run co blah blah. Therefore, it's pure all of these things, but with then the run co blah applied to it. So so it would still be nice to see the following transformation, which is the one where Perco also then becomes runco, and let's do that. Runco, and then COW is this thing, is that guy, the one at the end, NGCO, and then map of flip runco, because F is now flip runco on W, which is on runco free W. Right, so that's the idea. And then here we actually unpack it and put Cotis inside and hold our breath. Right. So that's going to be more tricky because the M actually the M is an effect of, it is an effect of the W that we want to get. And Rapco free W. Let's see what I did when I tried to do something similar with the ink. I did just get compose M, and then this is the base functor. This is not the W, but that's because I'm not in the co-free thing here. So I get just the direct base functor, not the co-free Comonad value. This should work, I think. So what is this saying? You're saying you want M4 R1. R1 being bound at line 264, column 52. Am I right that Coty is composed blah? I mean, it sounds like it is, but here it's the end monad that we're creating. Hold on, what does that even mean? Yeah, I think we're saying we can unwrap a functor layer to get the monad, right? And so with Coty we get the comonad, wrapped in an M, right? Yeah, no, not exactly, right? So when we unwrap the Coty, we get this WAMR to MR function. So, right. So this M we need to apply to something. And I think that's what this whole malarkey does there. Okay, hold on. Can we just do W and then say, yeah, that's what we meant. Like that. Not, yeah, not too bad. Qt compose mfm, Qt wm. Can we do something like that? Is that better? Not so clear that it is. Because in theory, do I rewrap things into, because the W here, is it really W or am I missing something? That's the W is, oh, the W is this, right? But the W of the final thing, I think, the thing we're trying to create. Yes. And that's the functor that wraps things. So if that's the W, then that's why it needs to be unwrapped co-free first before getting into the thing. And so I suppose maybe I need to get the W by unwrapping the co-free of M. No. Oh. Uh-huh. Interesting. Oh, now we have a compose of compose. Yeah, that's not good, right? We don't want that. How come? Is it just an M? And we just unwrap it? And then what is the problem here? What could it be? Well, apparently this is not so good either. M is not a, yeah. Okay, compose M. And then W has type T0, T0 not showing up anywhere here, so that really doesn't help us. But then compose T3, T4 with type W. I mean, it kind of makes sense that we can't unwrap co-free here. Okay. And when we do this, is it rebuilding? I thought we had something that compiled that looked quite a bit like this just a second ago. What's not... we type COTW0. So, okay, so are we saying... Because what you're saying is this, I think, here. And I don't disagree with that. But... no, that's not what you're saying. Okay. This thing needs to rebuild a compose thing. I suppose, right? If we unwrap the compose inside the COTI, okay, I need to look at this again. If we unwrap the compose inside the COTI, the compose you know what, that's not right here. I don't think it should. I don't think there's compose here. No, I don't think there is actually. GCO. Okay, let's try something else. Are we saying... So this is not GCO. This is something different here. This is... what is this? Is this really this whole thing? No, because it's an F. Maybe there's not a co here. Yeah, I think I unpacked this wrong, and I need to fix that. Do I want to start with the co case? I think I do. So let's go back here again. So we're saying it's FMA to MA. And here, it's F co-WA to co-WA. Actually, it's co-F. And it just happened that W is co-free. So let's unwrap it further. It just happens that W is co of co-free F. That's what W is. But maybe we don't care. Now let's try the same trick here. Here we do have COTI, so that it makes sense to have COTI of F M and the A being this co-WA, or well, co-TWMA, returning on co-TWMA. I think that makes more sense. And then it just happens that W is this whole crazy thing. But what this means is that Coty FMA here, yeah, I think that's right. FM, and then that's the A that surrounds it, right? So, and the principle in this form, if we look at this, so it takes the what's called the GCO here is this co-WA, and we're trying to build a co-WA, right? So we try and build a co-WA, getting its monad, and then we unwrap. So we unwrap co-free W. I need some kind of type for co here. Co is run co. Okay, let's get co again. Co. Co is AMR to R, right? We need to have it somewhere here. Co WA is co for R, WA to R, R. And therefore, when we're here, we're really trying having a function of this type here, right? So it's a W that wraps A to R's. So when we unwrap co-free, we have our WA to R becomes something with the F in front. The F of the comonad, the co-free comonad, is it just, that's just F, that's not co-F or co-TF, that's I think F. And so when we map the thing underneath, that's fine. And then oh boy, so difficult. Run co. Let's get run co again. Yeah, let's run co. Here. So run co takes this thing that's a co. How is it a co? Yeah, it's a co of the base functor f with a co-WA inside. Okay, it is a co. And so that's an f. That's just f. And it's a f of A to R to R. It's really an f of co-W. Okay, let's try and write this down. Run co. Oh boy, what am I doing? run co is of type W co WA to WA to R, but this thing is actually F, and this is actually code WA, right? From this. That's what Web3 receives. So this, what's called GCO here, really is a co-F of code WA. So continue replacing co WA here, W is F, and then that's it. So run co GCO is now a function from an F, co WA to R, to an R. So where we pass it is this thing in order to get to our R. And we want our R to be something specific. We want our R to be whatever co must return, which therefore is the co WA. So I think we want R to be co WA actually. Which is a bit weird, but maybe. So when we pass it a flip run co, we're expecting a W of A to R. Unwrap co-free, I think, allows us to go underneath the F. But yeah, but it's all of these inversions there are getting lost again. So difficult. Okay. GCO is of type coef co WA, right? Coef co WA. We know that. We're cool. This co should be this. So when we pass it a function like this, apparently unwrapping it is going to work for some reason. Yeah, because this is the WA to R here. Okay, so what I'm saying, I think, is that this W has type WA to R. And so when the unwrap co-free W puts an F in front, which F? Right, so I thought that it would be just the F because we're in the land of the co-free comonads, and I think f is the base functor of the co-free comonad. That's what comonad co-free fw means. So therefore, the type of this should be f of w a to r. And so when we map underneath it, well, what is flip? So what's flip run co? It's actually less difficult when you use this method. I don't know where I picked up this method, but it actually works pretty well. So run co is this. Actually we have it right there. And like so, and therefore flip run co. Oopsie, what do I need to do? Stay here, go back, do this, and do not this. Do this, yes. So flip run co is w a to r co WA to R, right? So when we flip, then we go underneath the FWA to R, and yes, so when we do this whole crazy thing, then we are actually transforming co WA to R. We're doing a, so we're going under the F. We find WA to R's under the F. We transform them, so I think it means we get an F of co WA to R, because we transform our A to R into co WA to R's. Does this make sense? I don't know. We will see, because now we have the second run co. And what does the second run co do? Second run co. Oh, we have it over there. So hold on one second. Let's bring them down. We have these two guys here. And are those what we want? Well, run co takes this co WA. So the run co here, that doesn't work actually. What? The GCO. Note that it's still possible that I made a mistake unpacking this. The GCO is this co-F, co-WA. When we run code that thing, are we saying that the F becomes W and the A becomes co-WA? I think we might be. So the F becomes W, the W becomes F, so this becomes F, and this becomes co-WA, and then this becomes co-WA. And our types line up. Okay. So now we try and do the same thing for co-T, and obviously that's going to be a whole other difficult thing, right? we'll probably do that next time. Here we are, we know what we want wrap3 to do as a type. We want it to do this. Let's double check, because we said that wrap3 here was that co3 co-WA, and here we say, yeah, that's all wrong, right? So it's co of f co-WA to co-WA. And therefore this is co-T of f of co-WA m to co-T of co-TWMA. And that's right. And then this we can keep elsewhere. And therefore that's also co-T, not at all, not that. So this means that our GCO is of type co-TF co-WA. So we need something that's probably going to be run co-T, but that does this. Co-TWMA TWMA. The F is the F. This is co-TWMA. This is R. This is R. And then the question is that run co-T or not? And what's run co-T? Run co-T is this. F and M. Oh, right. Okay, the M wedges here. Okay, it's fine. And then the A is the co-TWMA. That's also fine. And then in that case, the F being the F is fine. The A being the co-TWMA to RMR. That all works out. That's good. Okay, but then right, but then since we have co-T here, we know that the whole thing is co-T FM co-TWMA. You know what? I think I need a little bit of extra real estate here. Co-TWMA, F is F, co-TWMA. Oh, to MR. Right? That's type signature of co-T. Okay, so that's the type signature of wrap3. Cool. So so we know our GCO here is a co-T FM co-T FWMA. Yes, it is, and it works. That's good. Yeah, we're going to need to indent everything a little bit to the left. Okay. So we know that WA is to MR, right? Yes, we do. So that's good. So the so the unwrap co-free, obviously we're going to have some trouble. And that's exactly where we were. So in order to extract an F, which we'll want to be A to MR, Well, you know what? No, that should just work. It's just that this W here, I'm doing the general case, by the way. I don't know whether that changes anything or not. I haven't added the compose MF. I'm just doing F here, I think. And it could be that that's fine. It could be that that's it's not enough to make this type check. It is. Oh my. Okay, but hold on. If that's enough, then but it doesn't solve this problem, right? Because the wrap free, where are you? Here. Hold on, that's it might actually, because here we're saying what, compose M counter space, I think, right? Are we though? Yeah, that's unclear. We need to define M. Could say full M, monad M. See whether that works or not. Whoopsie. And that doesn't work. I think because component is not, we need like some kind of component T, in fact. Maybe in the same spirit. So, but I think it seems like we've got rid of that that type error. That's pretty amazing, though. So, wow, excellent progress. That's a perfect place to stop. That means next time on Saturday, probably, or maybe Sunday, I will catch up on how to make our components be able to deal with this base effect. And I think I'm more or less retracing the steps of Arthur Xavier here, who did go towards a component T that did have an M there wedged. In fact, the component also had an M. It's a component T had a base wedged in there. And I think we probably have to do some similar trick there, but now that we're using a slightly different construct, it's going to be also a slightly different approach there. But it's probably going to look like it a little bit, I suppose. Maybe we'll have a component TM counter space or something. And maybe we'll know how to interpret that. The fact that I'm passing the interpreter here and that doesn't show up in the type is a little bit weird. I think it could be that that's maybe just what's the problem here. Boom. It's actually that problem, sort of. And so hold on, right, because step counter needs to be past an interpreter, like so, right? And then this, yeah, co-free and compose. So are you saying that we can do that? Because I prefer to do that if it's possible. No, because you need an M. Okay, that's fine. I can give you an M. And here, okay, you want effect here. Why would you want effect though? Because counter space is implemented with effects. And you know what? We could make this M. Maybe not. We can't because our UI needs M, but we can give it M. And then wrap free doesn't work again. I see, because we don't have M up there now. Okay, so you know what? I'm going to backtrack. And I'm going to say that instead of making things more general, I'm going to make things, for now, more constrained. And I'm going to say this is effect. and apparently that is upsetting somewhere here. And then that's affected identity. Okay, and then I think now we're in the realm of dealing with the fact that component is based on co things, not co t things. Okay, fine. Maybe that's what we do. We say component m w co t w m unit, and we import trans and co-t and run co-t, and then so hold on, component like this doesn't compile, right? Unknown type co. Yes, so right, this input thing, you know what, I kind of want to get rid of it now. I'm not sure that it's relevant anymore, so let's get rid of it. Input, bye bye, and T WM unit with component M, and I suppose maybe we want M to be a monad, but and then we just run Coty with that and hope that it works. It's not just going to exactly work, probably because we need to do something with that M. And it could be that we just do M run Coty something. Not exactly that. But I think that's yeah, that's progress again. Maybe we need to say monad M. But in any case, I'm going to, I think I'm getting way closer, and I'm finally unblocked, I think, on this pretty hard to write type class. Turned out that I only needed to, yeah, now that I look at it that way, it just makes so much sense. I don't need to deal with the composed things. I just need to deal with the fact that W is a co-free comonad with base functor F. And that's what comonad co-free gives us. And then wrap free just tells us that the co-t of those are also valid, meaning that, to spell it out, the co-t WM free monad has base functor co-t FM. Yep. So very happy that we got that sorted. This actually was quite helpful, right, to get the type to align and give us a bit of an aha moment. I'm going to just maybe make a note of what we did and where we're going next. And I realize I haven't even created a folder for today. So let's do that. And it was in Comonad things. And so what did we do? We did we implemented the monad free instance for co-t FM co-t WM. And so next, we'll implement component T WM, or in fact, explore for components WM. All right, and we will cross that. Excellent. Thanks a lot for watching, and More Comonadic Explorations next time on Saturday or Sunday. Take care. Bye-bye.